So the next problems are from, section 11.2. So people ask for pretty much all the problems in number 2. So 2a gives us the summation n equals 0 to infinity of 1 over the square root of 2 all to the n power. So if you have a number to the n power, and that's all you kind of have in your problem, it's going to be a geometric series. So this is a geometric series. In this case, the r is 1 over the square root of 2. And the absolute value of r, which is just going to be 1 over square root of 2, is less than 1, which says that the series converges. Oops, spelling it wrong. Converges. And anytime a geometric series converges, you can find the sum. And the sum, I always said, is the first term divided by 1 minus r. So in our case, the first term is going to be 1 over square root of 2 to the 0 power. And the reason that is because n is 0 for our first term. And then we're going to divide that by 1 minus 1 over the square root of 2. So this is going to be 1 divided by 1 minus 1 over root 2. Probably the easiest way to take care of this, which is different than I did on the review sheet, is to just multiply the top and bottom by root 2. So if I multiply both, I haven't changed the problem. On the top, I end up with root 2. On the bottom, when I distribute this root 2, I have root 2 times 1, which gives me root 2. And I have root 2 times minus 1 over root 2. So the root 2's there would cancel out, and I just get minus 1. So that's how I got that sum. Okay, so 2b, I have the summation n equals 0 to infinity of the cosine of n pi. And so if I look at this one and I say, okay, the cosine of n pi, it's not a geometric series. It doesn't really follow kind of any of the series rules that I know. So I'm going to try the divergence test first, and maybe I'll get lucky. So if I try the divergence test, we look at the limit as n approaches infinity of the cosine of n pi. So as I put in infinity here for n, the cosine, remember, it just oscillates back and forth. So it keeps going up and down and up and down and up and down and up and down forever. So it doesn't have a limit as it goes towards infinity. That's why I put the limit does not exist. So GNE does not exist. And that's why I put underneath it, because it oscillates. And so does not exist is not equal to 0, so by the divergence test, it diverges. And if I look at 2c, so looking at 2c, we have the summation n equals 0 to infinity of e to the negative 2n. So if you look, I have a power of n. And so what I really have here is I have the summation n equals 0 to infinity of e to the negative 2 all to the n power. So this is a geometric series. R here is e to the negative 2. Remember, e to the negative 2 is 1 over e squared. It's positive, so, and it is less than 1. So that means it converges. And since it converges, I can find the sum. So the sum is going to be, again, the first term. So we're going to have e to the negative 2 to the 0 power, all divided by 1 minus e to the negative 2. So e to the negative 2 to the 0 power is 1. So 1 over 1 minus 1 over e squared. Just like in the problem on the last page, I'm going to multiply top and bottom by e squared to get rid of that complex fraction. So I have e squared over e squared minus 1. So that is what the sum would be. Okay, so looking at 2D, So 2D, I have the summation n equals 0 to infinity of 2 to the n minus 1 over 3 to the n. Okay, so if I looked at this now, knowing all the series tests we know, I would probably actually maybe do a comparison test. But in the section this is in, the only tests you know are telescoping tests, divergence tests, and geometric series tests. So this kind of looks like a geometric series. I could actually split it up, though, into two series. So it's a series n equals 0 to infinity of 2 to the n over 3 to the n minus 1 over 3 to the n. And both of those are geometric, and I could actually split it up into the summation of the first series. So we'll add up all the 2 to the n over 3 to the n terms, and then we'll subtract off the summation of the second series. Okay, so, and if I write this even a little bit more so it looks like a geometric series, we're going to have 2/3 to the n power minus the summation n equals 0 to infinity of 1/3 to the n power. So both of these are geometric. In this first one, r is 2/3. That's less than 1, so it's going to converge. In the second one, r is 1/3. That's also less than 1. So they both converge. And the sum is just going to be the sum of each one, then subtracted. So the sum of the first series is going to be 2/3 to the 0, first term, divided by 1 minus 2/3, and then minus the second one. So let's figure out what this first one is here. So this is going to be 1 over 1 minus 2/3, and just like I've done in these last problems, multiply by 3, multiply by 3. So we're going to end up with 3 over 3 minus 2, so 3 over 1, or 3. And then in my second series, we're going to have 1/3 to the 0 divided by 1 minus 1/3. So we're going to have minus 1 divided by 1 minus 1/3. Same thing, multiply the top by 3, multiply the bottom by 3. So we're going to have 3 over 3 minus 1. So we're going to have minus 3/2. So we have 3 minus 3/2. And 3 is the same as 6/2, so 6/2 minus 3/2, which would end up being 3/2. Okay, and then the last one here, 2e. So I have the summation n equals 1 to infinity of the natural log of n over n plus 1. So again, what I did on the solutions was I looked at it and I said, okay, well, it doesn't look like a geometric series to me. It doesn't look like a telescoping series to me right away. So I might as well try the divergence test first. So if I try the divergence test, we're looking at the limit as n, oops, that's a terrible looking n, n approaches infinity of the natural log of n over n plus 1. So if you plug in infinity into n over n plus 1, this limit is going to turn out to be 1 because the power on the top and the power on the bottom are the same. So this is going to be the natural log of 1, and the natural log of 1 is 0. So that's sad because the divergence test didn't tell me anything. So I have to try a different test. So it's definitely not a geometric series. And at this point, the only other test we have is the telescoping series where things cancel out. And you might go, well, how am I supposed to get stuff to cancel out? And so the trick to this is to remember that the natural log of n of a fraction is really the natural log of the top, so the natural log of n minus the natural log of the bottom, natural log of n plus 1. So we're taking the series of that. And if I begin to look at these, what happens? So if I plug in n equals 1, I'd have the natural log of 1 minus the natural log of 1 plus 1, right? Then if I plug in n equals 2, I'd have the natural log of 2 minus the natural log of 2 plus 1. So this part here was from me plugging in n equals 1. This is from me plugging in n equals 2. And you could keep going. You could keep looking at multiple pieces of this. So plus, we'll do the next term. The next term would be the natural log of 3 minus the natural log of 3 plus 1, right? So this is the n equals 3 term. And we're going to keep going, right? So there's this generic term, the natural log of n minus the natural log of n plus 1, right? And we will keep going. So if you look at these, oops, I'm going to come over here so I have more room. We really have the natural log of 1 minus the natural log of 2. That's all from the first piece. From the second piece, I have the natural log of 2 minus the natural log of 3. From the third piece, I have the natural log of 3 minus the natural log of 4. And I keep going, right? Natural log of n minus natural log of n plus 1. So if I look at this, this minus natural log of 2 cancels out the natural log of 2. Minus natural log of 3 cancels out the natural log of 3. Minus natural log of 4 would cancel out the next term. So this natural log of n would end up getting canceled. And so this is really going to be the natural log of 1 plus the limit as n approaches infinity of minus the natural log of n plus 1. And if you plug that in, you would end up with 0 minus infinity, which is minus infinity, so the whole entire thing diverges. Okay, so I forgot to do 1D from this section. So 1D is the summation n equals 1 to infinity of 1 over the natural log of n plus 2 minus 1 over the natural log of n plus 1. Okay, so this is one of those telescoping series. It's already been broken into fractions for us. So we want to think about plugging in values. So if I plugged in n equals 1, I would have 1 over the natural log of 1 plus 2 minus 1 over the natural log of 1 plus 1. Then if I plugged in n equals 2, I would have 1 over the natural log of 2 plus 2 minus 1 over the natural log of 2 plus 1. If I plugged in n equals 3, I would have 1 over the natural log of 3 plus 2 minus 1 over the natural log of 3 plus 1. And keep going, we'd come up to this 1 over the natural log of n plus 2 minus 1 over the natural log of n plus 1. Okay, so if I work this out, I have 1 over the natural log of 3 minus 1 over the natural log of 2 plus 1 over the natural log of 4 minus 1 over the natural log of 3 plus 1 over the natural log of 5 minus 1 over the natural log of 4 plus 1 over the natural log of n plus 2 minus 1 over the natural log of n plus 1. Okay, so if you notice, the first piece of this term cancels the second piece of the second term. The first piece of the second term cancels the second piece of the third term. This 1 over 1 plus 5 would cancel the second piece of the next term. So eventually, this second piece is going to get canceled because the second piece is what gets canceled out first. So in the end, we're left with minus 1 over the natural log of 2 plus, we need to take that limit as n approaches infinity of this n part, which is 1 over the natural log of n plus 2. And the natural log of n plus 2 would go to infinity, but 1 divided by infinity is 0. So this is going to go to negative 1 over the natural log of 2 plus 0, so minus 1 over the natural log of 2. So that's how I got that one. So these next set of problems come from section 11.3. The first one is number 5. So number 5 gives us the summation n equals 2 to infinity of the natural log of n over n. And so if I look at this, it's not a geometric series, it's not a p-series, it's not a telescoping series. So at this point in the sections, the only two things we have left are the divergence test and the integral test. If you were to do the divergence test, you would find that the limit would end up turning equal to 0. So this is going to be an integral test, and that makes sense because looking at it, I know how to integrate it. So we're going to do the integral test. Our function f of x is going to be the natural log of x over x. I just have x's instead of n's. And so we know it's positive, right? Natural log of x is going to be positive for x being 2 or bigger. It's decreasing. So it's positive, it's decreasing. And now we have to take the limit, or now we have to do the integral. So we're going to look at the integral. Before I do the integral, we should also say it's continuous. So if you were to look at a graph of natural log of x over x, you would see it's continuous. So we're going to look at the integral now from 2 to infinity of the natural log of x over x dx. And that's going to be equal to the limit as b approaches infinity of the integral from 2 to b of the natural log of x over x dx. And if I come over here and I just do the integral, so the natural log of x over x dx, if we let u be the natural log of x, du is going to be 1 over x dx. So this whole integral is just going to turn into the integral of u du. And the integral of u is u squared over 2. So this is going to be the limit. I have to go back to x's, right? So it's going to be natural log of x quantity squared all over 2. So we're going to take the limit as b approaches infinity of the natural log of x squared over 2 evaluated from 2 to b. And so if we plug in b, we have the limit b approaches infinity of the natural log of b squared over 2 minus the natural log of 2 squared over 2. And if I plug in infinity, that first piece is going to end up being infinity. The second piece is this natural log of 2 squared over 2. So the whole entire thing is infinity, which means it diverges. So the next one from section 11.3 is number 7. And so if I look at 7, it says the summation n equals 0 to infinity of negative 2 over n plus 1. Okay, so if I look at this, it's not a geometric series, it's not a p-series, it's not a telescoping series, so all I'm left with so far up until this point is the integral test or the divergence test. If you took the limit of the divergence test, for the divergence test, you would get 0. So we're going to try it as an integral test. Now the problem is to do the integral test, you have to have a positive, yes, the function used has to be constant, positive, and decreasing. And so that negative 2 in there does not help anything. But I can pull the negative 2 out in front. So we have negative 2 times the summation n equals 0 to infinity of 1 over n plus 1. And so now if we let f of x be 1 over n plus 1, we know that this is a continuous function. We also know it's positive, and it is a decreasing function. So we're okay to use the integral test. So we're going to look at the integral from 0 to infinity of 1 over x plus 1 dx. And so this is going to be the limit as b approaches infinity of the integral from 0 to b of 1 over x plus 1 dx. So you could use a u substitution. We talked about these back when we did partial fractions. And so if you didn't want to use the u substitution and you just recognize this is just going to turn out to be the natural log of the absolute value of x plus 1 evaluated from 0 to b. So we're going to have the limit as b approaches infinity of the natural log of b plus 1 minus the natural log of 0 plus 1. So this is going to be the limit as b approaches infinity of the natural log of b plus 1. The natural log of 0 plus 1 is 1, and the natural log, so this is going to be minus the natural log of 1. And so if I plug in b goes to infinity, I have infinity minus 0, which is just infinity, so it's going to diverge. So the next one is problem number 10. So I look at this, n equals 1 to infinity, n sine 1 over n. So if I look at this, again, it's not a geometric series, it's not a telescoping series, it's not a p-series, so that's leaving me with the integral test and the divergence test. This looks kind of annoying to integrate, so I'm going to try the divergence test first, and hopefully that works out for us. So we're going to look at the limit as n approaches infinity of n sine of 1 over n. And if you plug in, you would end up with infinity times the sine of 1 over infinity, right? If we're strictly plugging in here. So this is going to be infinity times the sine of 0. And the sine of 0 is 0. So we have infinity times 0. Remember, infinity times 0 is one of those indeterminate forms where I have to kind of rewrite stuff. So this is going to become the limit as n approaches infinity of, I'm going to leave the sine of 1 over n on the top. I want to push that n down to the bottom of the fraction, but I'm not allowed to change my problem. So I'm going to make this 1 over n on the bottom. And now, if you think about it, if I did keep the top, change the bottom to multiplication, and flip this fraction, I would end up with n sine of 1 over n. So it's the exact same thing I had before. And now if I plug in, I'm going to have the sine of 0 over 0 or 0 over 0. So now I can actually use Hopital's rule and get the limit as n approaches infinity. The sine of 1 over n is going to be the cosine of 1 over n, and then times the derivative of the stuff inside. So remember, 1 over n is the same as n to the negative 1. So the derivative is going to be negative n to the negative 2. And same thing when I take the derivative of the bottom here, it's going to be negative n to the negative 2. So these negative n to the negative 2 parts will cancel each other out. If I plug in infinity, I'm going to have the cosine of 1 over infinity, which is going to be the cosine of 0, and the cosine of 0 is 1. And 1 is not equal to 0, so it diverges. Which is good, I didn't have to use the integral test. Okay, so the last one in this section that people ask for is number 11. And in number 11, it asks for the summation n equals 1 to infinity of e to the n over 1 plus e to the 2n. So again, this isn't an integral test, it's not an integral test. It is going to be an integral test because if I tried using the divergence test, we would end up getting 0. It's not a geometric series, it's not a p-series, so it's not a telescoping series, so really all I have right now is the integral test. So if I look at the integral test, so the first thing I want to figure out, I'm going to let my f of x be e to the x over 1 plus e to the 2x. We're going to so it's a continuous function, it's positive, and it's decreasing. And so now we have to integrate the integral from 1 to infinity of e to the x over 1 plus e to the 2x dx. And so that's going to end up being the limit as b approaches infinity of the integral from 1 to b of e to the x over 1 plus e to the 2x dx. And if I look at that integral, so if I have e to the x over 1 plus e to the 2x dx, if we let u be e to the x, then du is going to be e to the x dx. And so this integral is going to become du on the top, and on the bottom I'm going to have 1 plus u squared. And so that's actually the inverse tangent, so it's the inverse tangent of u, or the inverse tangent of e to the x. So we're looking at the limit as b approaches infinity of the inverse tangent of e to the x evaluated from 1 to b. So the limit as b approaches infinity of the inverse tangent of e to the b minus the inverse tangent of e to the first. And so as b goes to infinity, right, this e to the b is going to go to infinity. So what we really have is we have the inverse tangent of infinity minus the inverse tangent of e. And if you remember the inverse tangent function, it looks like this. So as x goes to infinity, the inverse tangent actually approaches this asymptote up here, which happens to be pi over 2. So this is going to be pi over 2 minus the inverse tangent of e. And that's an actual number, right? It looks weird, but it is a number. So this is going to converge. So the next set of problems come from section 11.4. And so in section 11.4, the first one that people wanted to see was number 1. And so if we look at number 1, we have the summation n equals 1 to infinity of 1 over 2 square root of n, plus the cube root of n. Okay, and so in terms of this series, so in terms of looking at this, it's not a p-series, it's not a geometric series, it's not a telescoping series, it's not something I know how to integrate. So I probably want to try using either the comparison test or the limit comparison test. So when I do either the comparison test or the limit comparison test, one of the things I do is I try to kind of pick the biggest thing that's on the top and the biggest thing that's on the bottom. So I'm going to compare this to the summation n equals 1 to infinity. So the biggest on the top, all I have is a 1, so I'm going to keep the 1. On the bottom, I have two pieces here. So one is 2 square root of n, and the other is the cube root of n. So I'm going to pick the 2 square root of n. I know in the solutions I picked square root of n, you could use either one, but the bigger piece, so if you think about the square root of a number, the cube root of a number, the square root of a number is bigger. So I'm going to keep the 2 square root of n part. And I can think about this series really as the summation n equals 1 to infinity of 1 half times 1 over the square root of n, or that's really the summation n equals 1 to infinity of 1 half times 1 over n to the 1/2 power. And so this makes this a p-series. Our p in this case is 1/2, so p is equal to 1/2. 1/2 is less than or equal to 1, so it diverges. Okay, so now the question is you have to try to figure out if our series would happen to be bigger than this series that diverges. And if you worked it out, you would find out that our series is not. So the regular comparison test isn't one that works super well here. However, we could do the limit comparison test. So sometimes it gives us something that works when the regular comparison test doesn't. So I'm going to compare my old series, so 1 over 2 square root of n plus cube root of n, to 1 over 2 square root of n. And so by basically just doing keep, change, flip, this is the same as the limit as n approaches infinity of 1 over 2 square root of n plus the cube root of n times 2 square root of n over 1, or we have the limit as n approaches infinity of 2 square root of n over 2 square root of n plus cube root of n. And if I plug in, I end up with infinity over infinity. So if we do L'Hopital's rule, we get the limit as n approaches infinity. I have, remember, it's n to the 1/2, so 1/2 times 2 would just give me 1. So we have n to the minus 1/2 over, same thing, if I take the derivative of 2 square root of n, I'm going to get n to the minus 1/2. And the derivative of the cube root of n is going to be 1/3 n to the minus 2/3. And so if I kind of rewrite this a little bit, I have the limit n approaches infinity. I really have 1 over the square root of n, all over 1 over the square root of n, plus 1/3, and this is the cube root of n squared. And so what I'm going to do is I'm going to multiply the top and bottom by square root of n to kind of help me clear this out a little bit. So this is going to be the limit as n approaches infinity of 1 on the top, 1 on the bottom, and then we have here, we have plus square root of n over cube root of n squared. And so that's really just the limit as n approaches infinity of 1 over 1. So remember, this is n to the 1/2 power, and this is n to the 3/2 power. So we have 1/2 minus 3/2, which is -2. So, oops, this isn't 3/2. I wrote it the wrong way. It's 2/3. So you're going to have 1 minus n to the 1/2 minus 2/3. So we're looking at the limit as n approaches infinity of 1 over 1 minus n to the -1/6. And if I plug in infinity now, I'm going to have 1 over 1 minus infinity to the -1/6. So we're just going to have 1 over 1 minus 0, or 1, and 1 is positive and finite, so that means both series diverge. So the next problem is problem number 5. And in problem number 5, I did type the index wrong on the actual problem, so it should have said the integral from n equals 3 to infinity of 1 over the natural log of the natural log of n. So again, it doesn't fit any of our regular series. It's not a geometric series, it's not a p-series, it's not a telescoping series, it's not something I know how to integrate. If I tried the divergence test, I would get 0. So that kind of leaves me with the comparison test. And I gave the hint in class that you can always say the natural log of n is less than n. So in this case, I'm going to compare to the summation n equals 3 to infinity so if I look at the biggest thing on the top is a 1, the biggest thing on the bottom, I have these natural logs, but at the heart of it, I have an n. So I'm just going to take the n and see what happens. This is a p-series. P is equal to 1, which means it diverges. And so I want to ask myself, is 1 over the natural log of the natural log of n, is that going to be bigger than 1 over n? Since the series I'm comparing to diverges, I need my series to be bigger. And the answer is yes. So, and the reason why is because the natural log of the natural log of n, that's always going to be less than n. So 1 over is going to be bigger. So therefore, the series n equals 3 to infinity of 1 over the natural log of the natural log of n also diverges, because it's bigger than a series that we know diverges. So the next one is problem number 6. And in problem number 6, we're looking at the summation n equals 1 to infinity of the natural log of n squared over n cubed. So the first inclination that you may have is, so again, it looks pretty crazy, so we can try doing a comparison test. So compare to. So if you use kind of what I've been saying, which is take the highest thing on the top, so you might say, okay, well, I'll try n squared, and on the bottom, I'll try n cubed. So this is really the summation n equals 1 to infinity of 1 over n, and that's a p-series, and it diverges, right, because p equals 1. And then if I try to compare the natural log of n squared over n cubed to n squared over n cubed, I'm going to find that this is less than. So the natural log of n is less than n, like I said in the last example. And so this doesn't work, right? Because I have a series that diverges, but my series is smaller than that series. So there's actually, with natural logs, you can even do some other tricks. So you can say that the natural log of n is always going to be less than n to, is always less than, we'll call it, I don't know, the r root of n. So that means that the natural log of n is less than the square root of n. The natural log of n is less than the cube root of n. So sometimes if replacing the natural log of n with n doesn't work, sometimes replacing it with the square root of n works. So let's compare to the summation. So this time let's replace, instead of replacing it with n, let's replace it with the square root of n squared over n cubed. So that would be the summation n equals 1 to infinity of n over n cubed, which would be the summation n equals 1 to infinity of 1 over n squared. So it's also a p-series, but in this case p equals 2, which means it converges. Okay, so now we need to look at the natural log of n squared over n cubed, and we need to compare it to the square root of n squared over n cubed. So the bottoms are the same, but on the top, the natural log of n is going to be less than the square root of n. So the natural log of n squared over n cubed is going to be less than the square root of n squared over n cubed. So that's good. That's exactly what we want. So therefore, our original series, converges. So we're able to figure out what happens, which is nice. So the next problem we're going to do here is problem number 8. And problem number 8 is the summation n equals 1 to infinity of 1 over 1 plus the natural log of n. So again, as I said, you're going to kind of take the highest piece of the top in terms of comparing it. So this is, another series I don't have any idea really what's going on with it. So I'm going to try the comparison test. So the highest piece on the top is a 1. The biggest thing on the bottom is that natural log of n. And remember, we said how natural log of n is smaller than n. So we'll make the bottom 1 over n. So this is a p-series. P is equal to 1, so it diverges. So I did make a mistake in taking the derivative of using the limit comparison test on the solutions. So really, I'm just going to use the regular comparison test here. So I want to compare 1 over 1 plus the natural log of n, and I want to know, is that going to be bigger than 1 over n? And the answer is yes, and the reason why is because 1 plus the natural log of n is going to be smaller than n as soon as n gets pretty big, or big enough. That's going to work. So it doesn't work for n equals 1, but that's okay. It just has to work as you go far enough out in the series. So therefore, the series n equals 1 to infinity of 1 over 1 plus the natural log of n also diverges. Okay, so the next one people asked about was number 10. Again, number 10, I typed the index wrong on the homework paper, so it should have been from 2 to infinity of 1 over n square root of n squared minus 1. Okay, so if you look at this problem and I look at it and I go, okay, well, I'm not going to be able to integrate it. It's not a geometric series. It's not a p-series. It's not a telescoping series, so I might as well try the comparison test. And again, if you use my trick, right, so the first thing I would think to compare it to is 1 over n, and then times the square root of n squared. And if you do that, you would end up with the summation n equals 2 to infinity of 1 over n times n, or the summation n equals 2 to infinity of 1 over n squared, which is a p-series. P is equal to 2, so it would converge. So then the question becomes is 1 over n square root of n squared minus 1 going to be smaller than 1 over n square root of n squared? And the answer is no, right? So it's not smaller. So that means I have to pick something else. And the reason it's not smaller is because if you look at it, this n and this n are exactly the same. This piece here, the square root of n squared minus 1, would be smaller than the square root of n squared. So when I divide by it, this whole fraction is going to be bigger than this whole fraction. So what that means is I need to pick something else to try comparing it to. So this time, rather than, we're going to pick n equals 2 to infinity. So at this point, you're kind of like, just try something. So we'll keep the n, and this time rather than the square root of n squared, let's just try comparing it to the square root of n. So if we do that, this is going to be the summation n equals 2 to infinity. This is n times n to the 1/2, and so 1 plus 1/2 would be 3/2. So I have 1 over n to the 3/2. So it's also a p-series. P here is 3/2. 3/2 is bigger than 1, so it's also going to converge. And so now I want to figure out, is 1 over n square root of n squared minus 1 less than 1 over n square root of n? And so you could put it in a calculator or into Desmos and look at it. But in our case here, we can also say, okay, well, if I look at the bottoms, n is the same as n. The square root of n squared minus 1, that is going to be bigger than the square root of n, right? Because I'm squaring the n. So yes, this is going to be true because n square root of n squared minus 1 is going to be bigger than n square root of n. And that's true because the square root of n squared minus 1 is bigger than the square root of n. So therefore, our series, the summation n equals 2 to infinity of 1 over n square root of n squared minus 1 also converges. Okay, so people asked about number 11, which is the summation n equals 1 to infinity of 1 minus n over n 2 to the n. So this one's like a little ugly, and because you have that 1 minus, it's making stuff a little difficult. So I'm actually going to first off split this series into two pieces. I'm going to make this 1 over n 2 to the n minus n over n 2 to the n. And so then I can split this actually, and here the n's would cancel. So I'm going to have one series, which is n equals 1 to infinity of 1 over n 2 to the n, minus the second series, n equals 1 to infinity of 1 over 2 to the n. So this second series here, this is a geometric series where r is equal to 1/2, which is less than 1, so it's going to converge. So I know the second series converges. So now I kind of just need to figure out what's happening with the first series. So the first series here, we're going to use a comparison test on. So we'll compare it to the summation n equals 1 to infinity. Biggest thing on the top is a 1. The biggest piece of the bottom here is this 2 to the n. So we're going to try to compare it to that, which 1 over 2 to the n, we just said, right here was geometric and converged. So this is going to converge. And So if I compare 1 over n 2 to the n, I want to know, is 1 over n 2 to the n smaller than 1 over 2 to the n? And the answer is yes, because n 2 to the n is bigger than 2 to the n, right? So this denominator is bigger than this, and so 1 divided by something bigger is going to be something smaller. So that means that this first piece here also converges. So since our series is made up of 2 converging pieces that we're just subtracting, the whole series converges. Therefore, the original series converges. Okay, so the next one here is number 12. Number 12 gives the summation n equals 1 to infinity of 1 over 3 to the n minus 1 plus 1. And so, again, it looks almost like a geometric series, but I have that plus 1 part. So I'm going to try the comparison test. So compare to, and summation n equals 1 to infinity. Biggest thing on the top is 1. Biggest thing on the bottom, 3 to the n minus 1. So this is just a geometric series. So geometric, r in this case is 1/3, and 1/3 is less than 1, so it's going to converge. And then the question is 1 over 3 to the n minus 1 plus 1, is that smaller than 1 over 3 to the n minus 1? So if it is, then we know our original series converged. So if I compare these two, 3 to the n minus 1 plus 1, it's 1 bigger than this. So yeah, this is bigger than this, which means this whole entire fraction is smaller than this whole entire fraction. So yes, because 3 to the n minus 1 plus 1 is bigger than 3 to the n minus 1. So our original series, summation n equals 1 to infinity, 1 over 3 to the n minus 1 plus 1, also converges. Okay, and then the last one in this section, so number 13, asks for the summation n equals 1 to infinity of 10 n plus 1 over n times n plus 1 times n plus 2. So again, so if I compare to summation n equals 1 to infinity, the biggest piece on the top is 10n. The biggest piece on the bottom would happen if you multiplied all that stuff out. So you would actually end up getting an n from here, an n from here, and an n from here. So you'd end up with an n cubed. And so the n and the n cubed would cancel, and we'd have an n squared. So we have the summation n equals 1 to infinity of 10 over n squared. So that's a p series. P equals 2. 2 is bigger than 1, so it converges. Okay, so now I want to know, is 10n plus 1 divided by n times n plus 1 times n plus 2, is that actually going to be less than 10 over n squared? And so you can graph these and see that yes, it will turn out to be. The other trick you can do is you can always actually look at the cross product. So I can multiply these two together. So we'd have n squared times 10n plus 1 and ask ourselves, hey, is that less than the other one's cross? So 10 times n plus 1 times n plus 2. And if you did out the algebra here, you would get 10n cubed plus 1 on the left-hand side. On the right side, we'd end up with 10n times n squared plus 3n plus 2. Or 10n cubed plus 1, is that going to be less than 10n cubed plus 30n squared plus 20n? And so, yes, it definitely is. So then, is our original fraction less than the 10 over n squared? Yes. And so that means that our series converges as well. So the next set of problems comes from section 11.7. I will do section 11.6, but since we did 11.7 before 11.6, I figured I would do 11.7 first. So the first one people asked about was number 7. And so if we look at number 7, it asked us for the summation n equals 1 to infinity of the natural log of n over n. So you have a couple choices here. On the solutions, I did a comparison test. I did the comparison test because I don't really like the integral test that much, so I tend to use the integral test least often. You could use an integral test on this. This is one that would work for an integral test as well. So as long as you get in the end it diverges like I'm going to get using the comparison test, that's totally fine. But so you get some more exposure to comparison tests. So we're going to compare to the summation n equals 1 to infinity. So the bottom here is going to be n. And then this time I am going to actually pick 1 for the top. And so why I'm picking 1 is because then I get the series 1 over n, and I know what that does. That's a p series. P equals 1, so it diverges. And I know that the natural log of n is bigger than 1 once I get out far enough. And so because of that, that would mean that the natural log of n over n is going to be bigger than 1 over n, which is what we need. So therefore, the series n equals 1 to infinity of the natural log of n over n also diverges. So the next one, people asked about, I skipped number 2. People asked about number 2. Whoops. I'll do number 2 now. Sorry about that. So number 2 asks for the summation n equals 1 to infinity of n factorial e to the negative n. So anytime I have a problem that has a factorial in it, the first test I go to is always the ratio test. So if we do the ratio test, so for the ratio test, we look at the limit as n approaches infinity, and we always take the n plus first term, so that's going to be n plus 1 factorial e to the negative n plus 1, and we're going to divide it by n factorial, the original, e to the minus n. And now I'm going to do a little bit of algebra here. With the limit as n approaches infinity, I have n plus 1 factorial. The e to the negative n plus 1, that's going to move down to the bottom. And then on the bottom I have an n factorial, and then that e to the negative n is going to move to the top. And so I still have the absolute value of that. And now if I, and when I move the e down, it becomes positive, right? So it's now going to be positive e to the positive n plus 1. So I could do a little bit more algebra as well. So since I have an n factorial in the bottom, I want to think about breaking up the n plus 1 factorial. It's going to be n plus 1 times n factorial, e to the n, all over. E to the n plus 1 is going to be e to the n, e to the first, and then an e to the n. And so now I have a bunch of stuff that's going to cancel. My e to the n's cancel. I definitely didn't write that right, did I? So I had the e to the n on the bottom. This is the n factorial. But the e to the n's do cancel, and then the n factorials cancel. And so I'm left with the limit as n approaches infinity of n plus 1 over e. And if I take that limit, that ends up being just infinity divided by e, which is infinity. And so that is bigger than 1, so it diverges. Okay, so the next one now is number 10. And if I look at number 10, so number 10 is the summation n equals 1 to infinity of n factorial over 2n plus 1 factorial. So again, I have factorials. That tells me I'm going to do the ratio test. And the way that the ratio test is, it's the limit as n approaches infinity. It's the n plus 1 first term. So I'm going to replace everywhere there's an n, I'm going to put an n plus 1. So we're going to have n plus 1 factorial over 2 times the quantity n plus 1 factorial. And then on the bottom here, we're going to have n factorial over 2n plus 1 factorial. And if we do out the algebra, I have the limit as n approaches infinity. On the top here, I have n plus 1 factorial. This bottom is going to be 2n plus 2 plus 1. So it's going to be 2n plus 3 factorial all over n factorial divided by 2n plus 1 factorial. And then if I do keep, change, flip, in terms of getting rid of my complex fraction, we have n plus 1 factorial divided by 2n plus 3 factorial times 2n plus 1 factorial divided by n factorial. And now I can think about breaking down some of my factorials to get stuff to cancel out. So n plus 1 factorial, that I can think of as n plus 1 times n factorial, which is good because I have this n factorial on the bottom in the second fraction. 2n plus 3 factorial, I can think about if I broke off the first term, it'd be 2n plus 3. Break off the next one, it'd be 2n plus 2, and then I'd have 2n plus 1 factorial. And that's all times the 2n plus 1 factorial. And so now the n factorials would cancel, the 2n plus 1 factorials would cancel, and come up here, we're at the point where we have the limit as n approaches infinity of n plus 1 all divided by 2n plus 3 times 2n plus 2. And I dropped the absolute value because all of that stuff is positive. You could multiply the bottom out and then do Hopital's rule. So I kind of, on the solutions, I didn't take the time to do that. Just because I see that the power on the bottom is bigger than the power on the top, so I know the limit's going to be 0, but you could multiply this out, so you would have 4n squared, plus we'd have a 6n and a 4n, so 10n plus 6, and if I plug in there, I get an infinity over infinity. So if I do Hopital's rule, I get the limit as n approaches infinity, 1 over 8n, and then that is actually going to go to 0. We know that 0 is less than 1, so this is going to converge. So the next problem people want to see was number 11. Number 11 gives the summation n equals 2 to infinity of n over the natural log of n raised to the power n. So this is a little ugly, and I have that stuff raised to the power n. So because of that, that makes me think that I probably maybe want to try the root test. I could potentially do the ratio test, but then I'm going to have a natural log of n and a natural log of n plus 1, and so that's not going to cancel anything out real well for us. So we're going to try the root test. So the root test asks us to look at the limit as n approaches infinity of the nth root of the absolute value of n over the natural log of n to the n. So here we're going to end up being, we can remember the nth root we can rewrite as 1 over n. So this is going to be n over the natural log of n to the n, all to the 1 over n power. If I distribute that 1 over n, we have the limit as n approaches infinity of n to the 1 over n, all over the natural log of n. And then as n goes to infinity, so as n goes to infinity, we end up on the top. So on the top, we actually have to do that limit kind of separately. So, when I go to take the limit of the bottom, it's going to be equal to infinity on the bottom. But on the top, I kind of have to come off here on the side and do that limit separately. And I see that didn't show up on my solutions. So we're looking for the limit as n approaches infinity of n to the 1 over n. So if you look at that, that's actually infinity to the 0. And that's one of those indeterminate forms where we took the natural log. So we're going to look at the limit as n approaches infinity of the natural log of n to the 1 over n, which that's equal to the limit as n approaches infinity of the natural log, or 1 over n times the natural log of n, which would be the limit as n approaches infinity of the natural log of n over n, which is infinity over infinity. So if I do Hopital's rule, we get the limit as n approaches infinity of the natural log of n is 1 over n, or the derivative of the natural log of n is 1 over n. The derivative of n is 1, and so this is the limit as n approaches infinity of 1 over n, and so that becomes 0. And then since I took the natural log here, I need to redo that. So this is going to be, to get my original limit, we have the limit n approaches infinity of n to the 1 over n is going to be e to the 0, and e to the 0 is 1. So that's where I got that 1 over infinity. And then 1 over infinity is 0. 0 is less than 1, so it converges. And n to the 1 over n might have been one of those special limits I gave at the beginning that I said you're just free to use. I can't remember off the top of my head. So if that's the case, you are just free to use it too. Okay, so the last one from section 11.7 is number 14, and so the weird thing about number 14 is I didn't give you a nice closed formula for it. So in number 14, it's the summation n equals 1 to infinity of 1 times 3 times ... times 2n minus 1, all divided by 4 to the n, 2 to the n, and factorial. And so, again, it's got factorial. I'm going to use the ratio test. And so it's going to be the limit as n approaches infinity. So the top part, I'm going to replace n with n plus 1. So we have 1 times 3 times ... times 2 times n plus 1 minus 1. So all the ... means is kind of carry on the pattern. So like if you notice, really all we're doing is odd numbers, right? 1 times 3, the next one would be 5, then 7, and so forth. All divided by 4 to the n plus 1, 2 to the n plus 1, n plus 1 factorial. And all that is divided by 1 times 3 times ... all the way up to 2n minus 1. All divided by 4 to the n, 2 to the n, and factorial. Okay, so 2 times n plus 1 minus 1, this is 2n plus 2 minus 1, or 2n plus 1. Now, I'm just doing all the odd numbers, right? So every time you do an odd number, you keep adding 2. So the number that's actually right before the 2n plus 1, the number right before this, so like the number, say, right here, would be 2n minus 1, right? Because we just keep adding 2 as we move along the odd numbers. That's going to become important here in a second. So I'm going to write it actually that way. So this is going to be the limit as n approaches infinity. We're going to do the keep change flip. So 1 times 3 times ... and then I'm going to write the 2n minus 1, 2n plus 1, all over 4 to the n plus 1, 2 to the n plus 1, n plus 1 factorial. times, flip the second fraction, so 4 to the n, 2 to the n, n factorial, all over 1 times 3 times ... times 2n minus 1. So this is going to become the limit as n approaches infinity of, I have 1 times 3 times ... times 2n minus 1, 2n plus 1. All right, we're going to break up this bottom here a little bit. So 4 to the n plus 1 is 4 to the n times 4 to the first. 2 to the n plus 1 is 2 to the n times 2 to the first. And n plus 1 factorial is n plus 1 times n factorial. And then we have times 4 to the n, 2 to the n, n factorial, all over 1 times 3 times ... 2n minus 1. Okay, so now we got a lot of stuff that's going to cancel out for us here. All these numbers, 1 times 3 all the way up to 2n minus 1, they are all going to cancel. My n factorials are going to cancel. My 4 to the n's are going to cancel. My 2 to the n is going to cancel. So really I'm left with the limit as n approaches infinity of, on the top I have 2n plus 1, and on the bottom I have 4 times 2, which is 8, so 8 times n plus 1. So we have the limit as n approaches infinity of 2n plus 1 over 8n plus 8. And you could just realize that that limit is going to be 2 over 8 by looking at it, because the powers are the same. Or if you look at the limit, it would be infinity over infinity. And if I do L'Hopital's rule, we're going to get the limit n approaches infinity of 2 over 8. 2 over 8 is just 1/4. 1/4 is less than 1. So this series is going to converge. So this problem is from section 11.6. And this is problem 9. And it gives us the summation n equals 1 to infinity of negative 1 to the n, n squared, 2/3 to the n power. And it's looking for us to determine, does it converge absolutely, converge conditionally, or diverge? So I'm going to look at the absolute value first. So we're going to look at the series n equals 1 to infinity, the absolute value of negative 1 to the n, n squared, 2/3 to the n power. So that's going to be the summation n equals 1 to infinity of n squared 2/3 to the n. And so now I want to do a test on that series. And so I'm going to do the ratio test. I have some stuff raised to the n power, so I think it'll actually work out pretty decently. You probably could have done the root test as well. But I'm going to try the ratio test. So we're going to look at the limit as n approaches infinity of the absolute value of n plus 1 squared times 2/3 to the n plus 1 divided by n squared times 2/3 to the n. And stuff is going to cancel. The 2/3 to the n part here would cancel out all of that. And we're just going to be left with 2/3 to the first power. So we have the limit as n approaches infinity of the absolute value of n plus 1 squared times 2/3 all over n squared. And so if I take that limit, it's infinity over infinity. And so if I do L'Hopital's rule to it, we're going to get the limit as n approaches infinity of the absolute value. So the derivative of the top, the 2/3 is just going to stick around because it's a constant. And then I have 2 times n plus 1. And the derivative of the bottom is 2n. So this again is going to be infinity over infinity. And if I clean this up a little bit before I do L'Hopital's rule again, really I have 4/3 times n plus 1 all over 2n. And I don't need the absolute value there. So if I do L'Hopital's rule again, we have the limit as n approaches infinity. The derivative of the top is going to be 4/3. The derivative of the bottom is 2. 4/3 divided by 2 is 2/3. 2/3 is less than 1. So this converges. Okay, so remember, we started by looking at the absolute value series, and I found that the absolute value series converges. So since the absolute value series converges, that means, therefore, we converge absolutely. I will also make a note right now that, a bunch of people asked for number 10 because the answer on the review sheet or the answer on the solutions is not the same problem that was on the original, or on the homework sheet. I made a mistake typing up the homework sheet. The homework sheet problem is terrible, so you can ignore the problem on the homework sheet. If you want a problem to try, then I would try the one that's on the answers, right? So the one on the answers is okay. So yeah, that's all the problems that you guys asked for the sections in chapter 11.